Hello, in this video we're going to be talking about how to perform a hypothesis test about two means. The test statistic that we'll be using is t, and it's equal to x bar sub 1 minus x bar sub 2. That's one sample mean minus the other sample mean. This is not a typo. I wasn't able to get subscripts without the bar going over the subscripts, which is improper notation. And then minus the population mean from the first distribution minus the population mean from the second distribution. This is usually assumed to be 0 when we're doing a hypothesis test about two means. And then we divide that by the square root of s sub 1 squared over n1 plus s sub 2 squared over n2. The degrees of freedom. There's a more complicated formula that the calculator will use, but we're just going to use this simple case of the smaller of these two. What you will need to perform a hypothesis test is the same as we've always done: a statement of the null and the alternative hypothesis, a graph, the statement of reject or fail to reject the null, and then the conclusion statement. We'll also be looking at how to find a confidence interval for this. The error for this confidence interval is t sub alpha over 2 times the square root of s sub 1 squared over n1 plus s sub 2 squared over n2. Our first example, the accompanying table gives results from a study of the words spoken in a day by men and women, and the original data are in dataset 17 in Appendix B. We're going to use a 0.01 significance level to test the claim that the mean number of words spoken in a day by men is less than that for women. So our claim is that the mean for the men is less than the mean for the women. So that would be mu sub 1 is less than mu sub 2. The opposite, the mathematical opposite of less than, is greater than or equal to. So mu sub 1 is greater than or equal to mu sub 2. The null hypothesis is always equals, so mu sub 1 equals mu sub 2. The alternative is the claim or the opposite, whichever one does not have the equal sign. So in this case, that'll be our claim. Mu sub 1 is less than mu sub 2. Our degrees of freedom. N1 is 186, N2 is 210, so it's going to be N1 minus 1. So that's 185. Now that we have this information, we can find our critical value. I'll write down alpha first. Alpha is 0.01. In order to find the critical value, we'll need our alpha level. It's 0.01. We have a left-tailed test. That means our critical value is going to be negative. And we're using the t-distribution, so we'll need to pull up our t-table. So here's our t-table. We had a significance level of 0.01, and that's in one tail because we had a left-tailed test. So we want to use the second column in the t-table, and we had 185 for our degrees of freedom. In the table, we have degrees of freedom for 100 and 200, and so we'll use 200 because that's closest to 185. That gives us the critical value 2.345. And again, it's negative because we have a left-tailed test. So now we need to calculate our test statistic. The formula is t equals x bar sub 1 minus x bar sub 2. And you really, in the formula, there's really the subtraction of the population means, but that's assumed to be 0, so you don't even need to write that in there. And then we divide by the square root of s sub 1 squared over n1 plus s sub 2 squared over n2. Now plug in our numbers. X bar sub 1 is 15,668.5, and then minus 16,215.0, and then divided by the square root. S sub 1 is 8,632.5, and we need to square it, and then divide that by n1, which is 186. Plus, S2 is 7,301.2, and we need to square it, and then divide it by n1, which is 210. We will need this difference from the numerator when we're calculating our confidence interval. So type in 15,668.5 minus 16,215.0 and hit enter. It gives you negative 546.5. So we'll just need that down below for our confidence interval. So I just make a note of that. And then right after you hit enter, you're going to want to hit divided by and then the square root symbol. Make sure that you put these in parentheses when you're doing your calculations. You should get negative 0.6755. You can also use your graphing calculator to calculate your test statistic, and it will also give you a p-value. When you do this on your graphing calculator, I still want you to write out the formula for your test statistic, plug the numbers in, and then tell me what the test statistic is equal to. So you'll still need to show this work, even if you're doing it on your calculator. And the commands that you need to do this on your calculator is stats, tests, and then you want to sample t-test. You will need to provide x bar sub 1, S1, N1, and then also x bar sub 2, S2, and N2. You'll also need to give it the alternative hypothesis. And then for pooled, you want to say no. So the p-value that you should get is 0.2499. We could make a graph. Our critical value is negative 2.345. Our test statistic is negative 0.6755. Because our test statistic is not in the tail, we're going to fail to reject. And the graph, if you're going to do the p-value method, you would put alpha equals 0.01 here, and then your p-value would go here. Since we're failing to reject the null, which means that we're basically rejecting the alternative hypothesis. And so that means that we do not have enough evidence to support our alternative hypothesis, which is our claim. So you're always making this conclusion statement about our claim. And so now I'm just going to write out our conclusion. So there is not sufficient evidence to support the claim that men speak fewer words. So I'm just going to write that out. So here is our conclusion statement. There is not sufficient evidence to support the claim that the mean number of words spoken in a day by men is less than that for women. So again, we failed to reject our null. which in essence means we're rejecting our claim, and that means that we did not have sufficient evidence to support our claim. Now we need to compute a confidence interval. The error formula for our confidence interval is t sub alpha over 2 times the square root of s1 squared over n1 plus s2 squared over n2. For t sub alpha over 2, you always want to use the critical value that you find for your hypothesis test, and always positive, of course, when you're plugging it into this formula. So that would be 2.345 times the square root of 8,632.5 squared over 186 plus 7,301.2 squared divided by 210. Computing this on your calculator, you should get 1,897.1192. So now I need to subtract that from the difference above and also add it. So the numerator from our calculation above was negative 546.5. We want to subtract this 1,897.1192. When we do that, you should get negative 2,443.62. And then also add the 1,897. And there you should get 1,350.62. So our confidence interval, negative 2,443.62 and 1,350.62. Now, if you want to do this on your graphing calculator, you would click on Stats, Tests, and then it's 2samp t-int. You'll need to give it the following information: x bar 1, s1, n1, and then x bar 2, s2, and n2. You'll need to give it your sea level. For pooled, you want to tell it no. Also, one thing about the sea level, when you're doing a one-sided test like this, so I'm just going to draw out a little graph. We had a 0.01 significance level, so that means that this area is 0.01. This confidence interval is based on this test, so our confidence level is this area from here to here, and this is also 0.01 area. So this would be a 98% confidence level that we would want to enter in order to get this confidence interval off of our calculator. So it's just another thing for you to be careful about. 0 is contained within our confidence interval, and so because 0 is contained within that, then there is a possibility that the means are equal to each other, and so we would not be able to support the claim based off of that. So if this entire confidence interval were above 0, so the whole confidence interval were positive, then we might conclude that mu1 was greater than mu2 because our entire confidence interval was positive, and 0 is not in there, which sort of takes away the fact that the two means could be equal to each other. If the entire confidence interval was negative, then we might conclude that mu1 was less than mu2 because when we found the difference, we got all negative values, and 0 isn't in there. But if the confidence interval contains 0, then it is a possibility that the two means are equal to each other. In the next example, this is from data set 15 in Appendix B. It lists the arrival delay times in minutes for randomly selected flights from New York JFK to Los Angeles LAX. Statistics for times are given below. Use a 0.05 significance level to test the claim that Flight 1 and Flight 3 have the same mean arrival delay times. The first thing that we want to do is write out our claim and our opposite. The claim, Flight 1 and Flight 3 have the same mean arrival time, so that's mu1 is equal to mu2. The opposite then would be mu1 is not equal to mu2. So our null hypothesis is mu1 equals mu2, and the alternative is mu1 is not equal to mu2. So we have a two-sided hypothesis test. Alpha for this one was 0.05. The degrees of freedom for this particular problem, the ends are the same. They're both 12, so that gives me 11 for my degrees of freedom. Now we can find our critical value. So here's our t-table. We need the area to be in two tails. Our significance level for this test was 0.05, so we'll be using the third column over. We want that 0.05 to be in two tails because we have a two-tailed test. We have 11 degrees of freedom. So here's 11 degrees of freedom, and so that gives us a critical value of 2.201. This is a two-tailed test. We want both positive and negative, 2.201. Next, we need to calculate our test statistic. T is equal to x bar sub 1 minus x bar sub 2. Again, remember mu sub 1 minus mu sub 2 is almost always 0, so we don't need to write that out. Divided by the square root of s sub 1 squared over n1 plus s sub 2 squared over n2. X bar sub 1 is negative 20.5 minus x bar sub 2 is negative 15.08333. We're dividing that by the square root of S1 squared. S1 is 12.38401, and we're squaring that, divided by N1, which is 12, plus S2 is 15.62317, and we're squaring it, and then divide by 12. Again, don't do any rounding until the very end. We're going to need the numerator to do our confidence interval, so I'm going to make a note of that. The numerator is negative 5.41667. Don't forget to put these in parentheses when you're doing your calculation on your calculator, and you should get negative 0.9412. So now we could make our graph. Our critical values are negative 2.201 and positive 201. And our test statistic is negative 0.9412. Be careful of the number of decimal places. Again, when you're entering things into MyStatLab, it's really picky. Sometimes it'll change. Sometimes it'll want 3 decimal places. Sometimes it'll want to So just be careful and make sure that you're reading how many decimal places you need to give in MyStatLab. If you do this on your graphing calculator, then you will also get a p-value. The p-value that you get for this one is 0.3573, and that is greater than alpha, which is 0.05. And so both because our test statistic over here for the critical value method is not in the tails, it's in this middle portion. That tells us that we're going to fail to reject the null, and also when you have a big p-value, you also fail to reject the null. The error formula for our confidence interval is t sub alpha over 2 times the square root of s1 squared over n1 plus s2 squared over n2. Always use the critical value from the hypothesis test that you found above. For this problem, that's 2.201, and then times the square root of 12.38401 squared over 12 plus 15.62317 squared also over 12. When you compute this using your calculator, you should get 12.6686. Now we're going to subtract that from our difference from our calculation above. That was negative 5.41667. When you subtract that, you get negative 18.0853. 1, and then negative 5.41667 plus 12.6686, and there you'll get 7.25197. So our confidence interval, negative 18.085 up to 7.252. And just make sure that you're double checking on MyStatLab for the number of decimal places that they want, and also on your exams for class. If you're going to use your graphing calculator, you do get a slightly different numbers for your confidence interval. You'll get negative 17.39 for the upper 6.5547. And that's just because they have a more complicated way to calculate the degrees of freedom, and so they have a different t sub alpha over 2 number. Also, the confidence interval that you would get from your calculator for this first example is negative 2,437 up to 1,348. Sorry, 43.8. And then down here, 0 is contained within this confidence interval, so that would mean that we can't reject the fact that it might be 0, the actual one. So that's just how you would do that, and you're just going to have to answer a multiple choice question on my stat lab about the fact that 0 is not in that, or 0 is in this confidence interval, and so that means that there is a chance that the two means are equal to each other. So that is it for this video. I hope you're having a great day.